Hello everyone, I'm Tarun Prajit from CSEA, graduating in SYC. In this slide, let's see about navigating complex transactions in NoSQL. Welcome today, we will explore the unique challenges and opportunities presented by complex transactions in NoSQL databases. We will discuss how to design and implement solutions that ensure data integrity while maximizing performance and scalability. In this slide, let's see about challenges of NoSQL data models. First one is data consistency. Maintaining strong consistency in NoSQL is challenging due to its decentralized nature and the lack of a centralized transaction coordinator. This can lead to inconsistencies if data changes are not synchronized properly. Transaction isolation. Ensuring isolation of concurrent transaction can be complex in NoSQL databases. Data modification may not be immediately visible to other users, resulting in unexpected results if multiple transactions access the same data concurrently. In this slide, let's see about maintaining ACID properties. Atomicity, ensuring that a transaction either completes fully or not at all, even when spread across multiple nodes. Second one is consistency, guaranteeing the data remains consistent across all nodes, even during updates and failures. Third one is isolation, preventing concurrent transactions from interfering with each other, ensuring that each transaction sees a consistent view of data. Fourth one is durability, persisting data changes permanently, ensuring that they survive system failures and restarts. In this slide, let's see about strategies for complex transactions. First one is two-phase commit, a traditional approach that involves a coordinator and multiple participants. It ensures atomicity but introduces complexity and potential performance bottlenecks. The next one is optimistic locking, a technique that assumes transaction will not conflict. It checks for conflicts after the transaction is completed and retires if necessary. Third is sagas, a pattern that breaks down complex transactions into a series of smaller steps, each with its own compensating actions to handle failures. Next one is eventual consistency, a less strict approach that accepts temporary inconsistencies and relies on background process to eventually reconcile data. In this slide, let's see about atomicity and consistency. Atomicity. Each transaction is treated as a single unit of work. Either all operations succeed or none of them do, preventing partial data updates. Next one is consistency. Guaranteeing that data remains consistent across all nodes, even during updates. Different consistency levels, from strong to eventual, can be chosen based on specific requirements. In this slide, let's see about isolation and durability. Isolation, ensuring that concurrent transactions do not interfere with each other. Different isolation levels from read, committed to serializable are available to control the level of concurrency. Next one is durability. Once a transaction is committed, the changes are permanently stored, like replication and logging are used to ensure data persistence and failures. In this slide, let's see the use cases for complex transactions. First one is e-commerce. Orders processing involving multiple steps like inventory updates, payment processing, and order confirmation must be atomic and consistent. Next one is banking. Financial transactions such as transfers and payments require strict consistency and atomicity to ensure the accurate balances and prevent fraudulent activities. Third one is inventory management. Updating inventory levels across multiple warehouses or stores, ensuring that the total quantity is above consistent. In this slide, let's see about architectural patterns for transaction management. There are three: centralized coordinator, distributed consensus, eventual consistency with conflict resolution. Consensus. First, let's start with centralized coordinator, a single point of failure for coordinating transactions, suitable for simpler scenarios but prone to bottlenecks. Next, let's see distributed consensus, using protocols like Paxos or RAF to achieve distributed consensus, ensuring data consistency across nodes, require complex implementation. The third one is eventual consistency with conflict resolution, accepting temporary inconsistency and using conflict resolution to ensure eventual data consistency suitable for scenarios like consistency requirements. These are the three architectural patterns for transaction management. The three architectural patterns for transaction management are centralized coordinator, distributed consensus, eventual consistency with conflict resolution. In this line, let's see about real-world examples and lesson Lessons learned. First one is Amazon. Utilizes a combination of 2PC and Sagas for handling complex shopping cart and checkout transactions. The next one is Netflix. Employs eventual consistency with conflict resolution for streaming recommendations and content delivery, prioritizing scalability and availability. The third one is Twitter. Uses a distributed consensus approach to make integrity and consistency across its global success. We have come to the conclusion and recommendations. Trade-offs. Choose consistency models based on the specific needs of your application, considering the balance between consistency, availability, and performance. The second one is architectural patterns. Select appropriate architectural patterns for transaction management based on complexity, scalability, and fault tolerance requirements. Third one is testing and monitoring. Thoroughly test your transaction and monitor systems performance to ensure data integrity and identify potential bottlenecks. Thank you.